If you're the network administrator of a routed network, then you probably have some type of dynamic routing protocol in use. This is one that will automatically communicate between routers so that all of the routers know about all of the routes available on the network. They automatically provide subnet information to these routers, and using that information, the routers are able to find out what the best path might be to be able to forward traffic around your network. If there's an outage or a link goes down, these dynamic routing protocols can reconverge and build an entirely new set of routes that will work around the problems that may exist in your network. It's the router's responsibility to decide which path is the best path to take to get your traffic from point A to point B. But that decision has a lot of variables associated with it. Does the router decide what path to take based on the state of the link, or does the router determine how far away the particular connection might be and make its routing decisions that way? There has to be some type of formula that's used by the router to be able to gather all of this information about the network and be able to create a list of best routes to worst routes. If we're trying to decide on what dynamic routing protocol might work best in our environment, we also have to think about convergence. Some routing protocols are able to converge very quickly and keep the network up and running, and other routing protocols take an extended amount of time to be able to rebuild the routes that it needs to be able to operate. If we're connecting a number of different routers from different manufacturers, we may want to choose very standardized protocols versus some that might be proprietary to a particular manufacturer. Dynamic routing protocols that use a formula based on a distance to determine the best route are called distance vector routing protocols. With distance vector routing protocols, each router determines how many routers are between your location and the destination you're trying to get to. This number of routers is called the number of hops that a connection might be away from you. And the deciding vector of these number of hops is the distance that we're going to use. This means that if it takes 5 hops to get to a location, that's a much shorter distance than taking 10 hops to go another way. Making a routing determination based on that single metric of distance means that this routing protocol is relatively simple to get up and running. Works very well on relatively small networks, although it can be challenging to manage as the network grows much larger. A good example of distance vector routing protocols are RIP version 2, and Cisco's EIGRP. Here's an example of how we might use distance vector routing. We have Sam, who needs to send traffic to Jack. And between Sam and Jack are 3 different routers. There's a router 1, a router 2, and a router 3. You can see that router 1 and router 2 are connected to each other at 100 megabits, but router 2 and router 3 and router 3 and router 1 are connected at much higher speeds of 1 gigabit per second. With distance vector routing, the speed of these links doesn't matter. The only thing that's important is how many hops is the lowest to be able to get from point A to point B. So when Sam sends this information to router 2 knows that the lowest number of hops is going to be straight to router 1 and then to Jack. Even though the traffic may have gotten to Jack faster if it had gone to router 3 and then router 1, this distance vector routing algorithm chose the lowest number of hops, and that was directly between router 2 and router 1. Link state routing protocols are less concerned about the number of hops and more concerned about the quality of the connection between those two devices. If the network is up and running, you're able to get to that location. If the network is down, then you can't get to that location. And link state routing protocols also consider the speed of the link. A faster connection is going to have a higher priority than sending data over a slower bandwidth connection. As you can imagine, these are much more flexible routing protocols, so we tend to see them used on much larger networks. One popular link state routing protocol is OSPF, that's used on the largest networks in the world to be able to provide dynamic routing updates. With link state routing, Sam will continue to send this traffic to router 2, but router 2 knows that the fastest connection will be to send this traffic to router 3, back to router 1, and then finally to Jack. Some routing protocols use a little bit of link state and a little bit of distance vector and combine those together as the dynamic routing protocol. A good example of a hybrid routing protocol is BGP, or the Border Gateway Protocol, where it determines what route is best based on the paths, the network policies, or some pre-configured rule sets that you set inside of the router.